Alright, let's cover the next topic, which talks about the orbits and the speed of the planets orbiting around the Sun. Okay. Let's first talk about the orbital motion and its relationship to gravity. The gravitational pull can be defined as the action at a distance, where it's dependent on the mass or how large is the object that we are talking about, or how heavy, how dense it is, and also its distance from another object. This relationship is represented in our solar system by the Sun, where the Sun is the largest object in our solar system, and then hence everything in our solar system orbits around the Sun, including all the planets. Another form of orbital motion is seen by satellites. So we have natural and artificial satellites. The natural satellites are present in the form of moons that orbit around planets. So some other planets other than Earth also have moons that orbit around them, and we call those natural satellites. Artificial satellites are man-made, and they orbit around objects in space. So this can be like space telescopes and space stations that we send on missions in space so that we can observe the universe. Let's talk about the orbital motion and in specific the elliptical orbits. So most of the elliptical orbits that we see in space are present in forms of the planets or comets orbiting around the Sun, as well as the moon or the satellites orbiting around other planets. These are all forms of elliptical orbits, and we know that we can approximately simplify them into circular orbits just for the sake of simplification, but in reality they are all elliptical orbits. So in elliptical orbits, the center of rotation is not the Sun. In fact, there is a shift between the center of the Sun and the center of the orbit itself, and sometimes the Earth will be closer to the Sun than other positions in terms of its orbit, relative to the position of the Earth and the Sun in its orbital cycle. So in all calculations, you don't have to know how to do elliptical orbit, but you need to assume or simplify them into circular calculations, circular object calculations. And we need to study as well the speed. So most of the planets and the moons that we see in the solar system are visible because of the light being reflected from the Earth, and it's also coming from the Sun. So as we know, the outer regions of the solar system are really far, and we need to calculate what is the time taken for light to travel these huge distances. So there is a universal constant speed of light that we know about, which is 3×10⁸ meters per second. And if you know the speed, you can use the following equation to calculate the time taken for any distance to be covered by light. So you can rearrange the equation to put time as the subject and then divide the distance over the speed of light, and then you can calculate how long is the time taken for light to travel to that specific location. Now let's talk about how to find the orbital speed. So we said that most orbits happen in elliptical motion, but we're gonna simplify it to circular motion in this unit. For that, we need to calculate the circumference of the motion or the circle, and for that we need to find the radius and as well as use the circumference rule, which is 2 pi r, to find the circumference of a circle. And then we can use the formula, same thing, the speed equal distance over time, substitute our distance using the circumference formula, and then divide everything by the orbital period. And in that we will be able to calculate the orbital speed in meters per second, assuming that we take the radius in meters and time of the orbit in seconds. The center of the orbit has to be taken from the center of the object being at orbit, So center of the sun, in that case, in our unit, to the center of the planet. Okay. Now let's talk about some analytical data that we need to study. So over many years, we collected data about the planets and the moons, and also the sun, and how to find certain planetary data to study different conditions and the surface of different planets, their density, their temperature, and also how far are they from the sun. So we covered the orbital distance, which is the distance need to be covered by every planet to orbit around the sun for one full revolution. And also we covered the period, which is covered in days, the time taken for every planet to complete one full revolution around the sun. And then also some observation about the density and surface temperature of each planet and the gravitational field or the gravitational field strength on every planet. So note, we don't have to memorize all these information, but we need to understand and look for patterns, and also understand what is the effect of the distance of the sun relative to the planets in terms of increasing or decreasing, let's say, temperature, density, and also gravitational field strength. Yes. So if we make a quick observation, of course we know that the closer the planet to the sun, the lesser the orbital duration. So we know that Mercury will have the least orbital duration as it's very close to the sun, and then Neptune will have the longest orbital duration as it's really far from the sun. And then we can also talk about the surface temperature. So we know the closer we are to the sun, the more heat surface temperature we'll have, and then the furthest away from the sun, of course, the colder the planet would be. Except for if you make an observation at Venus, you can see it exceeds the surface temperature when compared to Mercury, even though it's further from the sun than Mercury. And that is because of the trapped carbon dioxide on its atmosphere, which makes it a greenhouse planet, or makes it trap more heat than the other planets. Yes. So in summary, we can say that the orbital duration is the time taken for the planet to complete one revolution around the sun. And we can simplify all elliptical orbits into circular path for the sake of simplification in this unit. And we can also say that the orbital duration will increase, it increases depending on the orbital distance. Hence, we can observe the difference between Neptune and Mercury in terms of the orbital duration. So the furthest away from the sun, you will experience a weaker gravitational pull, as we said that the gravitational pull is dependent on the size of the object and also the distance from the object. So the furthest from the sun, the less gravitational pull you will feel, which means that it will slow your orbit as well. And then we can say that the gravitational field strength does not just depend on the distance, it also depends on the mass, and we can say that the size doesn't really matter, that what matters is the mass. So even though Uranus is 4 times larger than Earth, but we can say that it has a smaller gravitational field since it's less dense, which means it has a lesser mass but a larger volume. So in terms of volume, Uranus is larger than Earth, but it has lesser density, which means it will have a lower gravitational field strength.